Yeah, shall we start?
Yes, sure.
So, hi everyone. Welcome to Network Seminar Series hosted by the Center for Network Intelligence at the EC and RBCCTS IAC. It's my pleasure to introduce today's speaker, Dr. Vipul Harsh. He will be speaking on failure diagnosis in network systems. Vipul Harsh graduated with a PhD from UIUC, where he worked with Brighton Godfrey. Is broadly interested in networked and distributed systems. His work spans failure diagnosis in network system, data center topology, distributed monitoring, and parallel algorithms. His works have been published on top tier CS conferences, and one of his projects has been adopted into product at VMware. He's currently a postdoc at Conviva Networks with Vyas Shekhar, where he works on failure diagnosis in internet scale services, among other things. We request the audience to keep your microphone silent for the duration of the talk, except while asking questions. Questions can be asked at any time during the talk. Please feel free to unmute yourself to ask your questions directly or type them in the chat box and we will relay them. Over to you, Dr. Harsh.
Yeah. All right. Okay. Thank you for inviting me. So I'll talk about failure diagnosis in networked systems. Um, so a bit about me, I'm broadly interested in distributed and networked systems. I finished my PhD at UIUC with Brighton Godfrey, and currently I'm a postdoc at Conviva, which came out of an came out of academic research. And a long time ago, I was an undergrad at ITB. All right. So network systems are becoming increasingly complex. You have your large distributed services, your microservice applications, which have thousands or tens of thousands of services even. You have your public or private clouds, your data center networks, WAN networks, enterprise networks, and so on. And these have very large scale with millions of components in them, and these components have complex interdependencies between them. And when you have such large scale, failures are inevitable. And here is a survey from Gartner which shows that the hourly cost of downtime and delays is more than $300,000 for the average enterprise. So there's a huge financial cost to these failures. And because of that reason, whenever these failures happen, operators have to quickly troubleshoot various types of failure scenarios using different types of telemetry sources that are available. And to help the operator resolve or diagnose these failures quickly, uh, there has been a lot of thrust on automated root cause analysis. And at a high level, this is about finding the entities that may have caused a problematic symptom. So I'm just trying to be a little bit broad here with the definition because this is used in a lot of different contexts. So your problematic symptom could, for example, be defined as a performance problem, or it might be a network issue, maybe it's a hardware bug, and so on. And your monitoring telemetry could also differ the data, basically the data that you have to perform the RCA. And from a research perspective, RCA offers a rich space of problems, but also from a commercial perspective or a real world perspective, it's of great interest and virtually has been implemented by all of the major cloud providers because it leads to faster resolution of issues. Okay, so while designing RCA, we need to be aware of the several complexities of network systems that exist today. So I'll just give a few examples. I already talked about this. So you have your microservice apps or your data center networks which could have, um, tens of thousands of components. Maybe, you don't have the exact dependency information between the entities in your system. For example, all you know is that service A is talking to service B, but you don't know whether service A depends on service B or vice versa, service B depends on service A. Or maybe the telemetry only consists of some aggregated view of metrics. For example, you have like some CPU usage or resource usage over every 10 minutes or 30 minutes, and it hides some instantaneous spikes. Or in a data center network, you don't know where your packets are going or which path the packets are taking because you have several equal cost multipaths that are available in class topologies in data centers. Or maybe you have cyclic dependencies between entities. This is actually quite common in real world systems. And this makes RCA very tricky. Or maybe there's some virtualization layer, and it's hard to even pinpoint the blame to either a physical component or a virtual component. So all this to just to uh, show you that doing RCA involves dealing with multiple of these challenges. And given that our systems are so complex, how do we design RCA that achieves the following goals? Like we want good inference accuracy. So, the solutions should be based on some robust, uh, robust solutions basically. We want them to be based on practical telemetry and use monitoring data that can be available in the real world, uh, that can be made available in the real world easily. And the RCA should have a reasonably fast running time. For example, if a human operator is trying to use this RCA system to diagnose failures quickly, a few minutes of running time is okay, but maybe a few hours is not. Okay, so to meet these goals, there are two aspects of RCA, and almost all RCA solutions will have these two aspects. So the first one is how do we model the behavior and interactions of system components precisely? So this is what I call as the physics of the system, right? And then using this model, how do you extract high inference for your root cause analysis? So this will involve like some sort of setting up training and inference algorithms. And sometimes you might need custom training and inference algorithms because of how your monitoring telemetry is, or maybe because of other practical constraints like scale and such. Okay, so there are two broad categories of related work. One are solutions that do not capture system behavior accurately, and this means that they do not they get restricted to very narrow set of environments. Like they do not work well if you change your environment. And there are also related works which do use an accurate model, but then the training or the inference algorithm does not handle the practical constraints of the real world. For example, it uses an accurate model, but it can only work with a small network. So you cannot use it, let's say, for a large data center network. Okay. So we have sort of two high level ideas or themes for RCA design. One is we'll use these powerful reasoning models to model complex interactions in the system. And we'll use this class of tools called probabilistic graphical models. So these are a class of probabilistic models that are defined on some underlying graph. And that graph may be directed, or maybe it's an undirected graph. And graphical models are a very natural way to model the various components in a distributed system. So we'll use these. And secondly, we'll develop some custom training and inference algorithms to handle the real world constraints. So these involve some algorithmic innovations. So with these three ideas, I've developed three systems. But in this talk, I'm only going to talk about the first one, but I encourage you to check out the papers for the others if you're interested. So the first one is Murphy, which is about diagnosing performance issues in distributed cloud applications. This appeared in SIGCOMM in 2023. So the goal here is to troubleshoot incidents in distributed cloud applications. So the system here could be, some applications, let's say in an enterprise network, or a private or a public cloud, or maybe it's a WAN. And you would typically have a large number of entities in your system. Like these would be your application components, your virtual components, your physical components, and these entities will may have like complex dependencies between them. And monitoring data would, in this case, is coarse-grained. So entities typically have metrics. So, for example, a VM might have a metric for CPU usage, and each of these metrics is a time series where each point is an aggregate over a few minutes. So that's the telemetry data that we have. And we want to automate troubleshooting using this telemetry. So first of all, let me define the troubleshooting problem a little bit more precisely. So I'll define it using an example that occurred in a production network. So here there was an application which stopped responding because its backend VMs were overwhelmed with high CPU usage. And here operators wanted to figure out the root cause of this problematic symptom. But more generally, we can define a problematic symptom as being as any anomalous metric of an entity, right? So for example, this would cover, it could be high response times for a user, or it might be high drop rate for a flow. And given this problematic symptom, we want to infer a root cause entity that may have caused this problematic symptom in this entire system. Uh, I mean, I'm only showing a snippet here, but there could be thousands or even tens of thousands of components in the entire uh, in the entire distributed system. So in this case, it turns out that the root cause was a crawler machine, which was sending a lot of requests to the backend and was trying to crawl the entire database. And that caused the backend VMs to have the high CPU usage, because of which the application stopped responding. So in this case, you can see that the root cause is a few hops away from the problematic symptom. And to get to the root cause, you need to have some idea of how these entities are interacting with each other. So this is very common. This is a very common question that arises when you are designing RCA, which is how do you model the interactions between your entities, or how do you model dependencies between the entities? And there are a spectrum of approaches here. uh, on one end of the spectrum are approaches like explain it, which assume no dependencies between entities. So these will treat the entire system as a bag of components. But that, but if you do that, then you lose a lot of information about the topological structure that captures how these entities are organized. So, for example, you know that if a VM resides on a host machine, then its metrics is more likely to get influenced by the metrics of the host. But if you do this, then you are losing out on that information. And on the other end of the spectrum are um, strict dependencies, are solutions that assume strict dependencies. Specifically, they assume that the dependencies are defined using a DAG, where you know how each component affects other components. And there are no cycles in this DAG. And if you have this partial order, then yes, the analysis becomes more tractable, but often in many cases, it is very hard to infer this DAG of dependencies between entities. So the if you don't have a DAG, you have some cyclic dependencies among entities. And we saw that, in fact, cyclic dependencies were the norm in our environment. And there are two reasons for having cyclic dependencies. One could be true cyclic influences. So, for example, uh, VMs will affect the metrics of the host machine that they reside on, but then in turn, the host machine will also affect the metrics of the VM. So this is like a true cyclic influence, and I think of this as the analogy here that I like to think of is how humans interact. It's very hard to impose a partial order in in among human interactions. So when humans interact, they not only give in that interaction, but they also take from those interactions. And the second reason is a more practical one. Sometimes, even if there is a directional dependency, it might be hard to infer the direction. So, for example, maybe service A depends on service B, but in your monitoring data, you are only seeing that service A is talking to service B and they're talking to each other, but you can't see further. So, it's hard to decide whether A depends on B or whether B depends on A. So, in such cases, we just over approximate the influence by assuming the dependency in both directions. And essentially, all application entities were observed to be involved in some cycle or the other. So there is really no getting around uh, this problem. So because of that, we decided that we don't want to ignore all of the topological structure that exists, but we also thought that assuming or obtaining a DAG in our environment was infeasible. So we went with some middle ground approach where we tried to incorporate some weak dependencies. And I'll talk about this in a minute. So with this idea, we designed a root cause analysis system for diagnosing performance issues. And so this is we designed this system called Murphy, which whenever a problem which where so we designed a system called Murphy, which does a three-part analysis to produce the root cause for an anomaly that's identified by an operator. So, for example, whenever an operator specifies a problematic or observes a problematic symptom, the operator can choose to trigger Murphy, and Murphy will run the analysis. So the first step in the analysis is to construct the model of the entities and the dependencies between the entities. And as I said, we want to model uh, the dependencies in such a way that we don't ignore the topological structure, but we also want to capture complex cyclic dependencies. And to do that, first we use this notion of a relationship graph instead of a DAG. So the nodes of this graph are the entities in the system. So these would be your flows, your application components, your VMs, your host machines, etc. And the edges are based on these loosely defined neighborhood relationship. So instead of a strict dependency, uh, we're just saying which entities are related to each other. So for example, there is an edge between a VM and its host. There's an edge between a flow and its source and destination endpoints, and similarly for other entity types. So this will give a very general undirected graph where we have actually captured the topological structure, but we have also allowed for cyclic dependencies. So this is the model that we're going to use. All right. So the second part is how do we find the root causes in this model? So recall what we want to do here is we have a problematic symptom in this relationship graph. So going back to the example that I showed you earlier, let's say we have a backend VM which is experiencing high CPU usage. So that's the problematic symptom. And we want to infer some other entity or maybe the exact entity or like some entity in this graph that may have caused that problematic symptom. And if this were a DAG, then the inference would be intuitive because you could look at all of the ancestors of the problematic symptom, and one of those nodes would typically be the root cause. But in this case, it's very hard to follow like how other entities might have impacted the backend VM. Okay, so we need a powerful algorithm to determine this causality in this general relationship graph. And we uh, designed this inference in two parts. So the first part learns a global distribution of all the metrics of all the entities in the relationship graph, and the second one runs a counterfactual reasoning algorithm using the distribution. So let me uh, dive into it a little bit deeper. So I'll explain this using a toy example. So let's say your relationship graph has five entities as shown, and each of those entities, I'm assuming that they have one metric. So for example, A has CPU usage, B might have something else. Uh, Murphy can handle like multiple metrics per entity, but I'm just showing you one metric per entity. And to learn the joint probabilistic distribution, we use this tool called Markov random field, which is essentially a probabilistic model, which is essentially a way to define a probabilistic model on top of an undirected graph. And an MRF is composed of many smaller models. And in this case, the smaller models determine the value of a node given the neighbors of a node. So, for example, the smaller model, the local model at B predicts the value of B given the values of its neighbors. So, in technical terms, this is known as the Markovian property, the which states that the value of B is conditionally independent of other nodes given its neighbors. Okay. So, this is the model that we are going to use, and we learn all of these local models using historical data, and because this is just this model just does metric prediction, we were able to test how good this model is for a large production data set, because we do not need any labeled failure examples, which is typically hard to get. But this one just predicts the metrics. Okay. So let's say now that we have a global distribution of the metrics, and let's say we want to figure out is whether A is a root cause for D's high CPU or not. So in this case, the problematic symptom is D's high CPU. And let's say the root cause candidate you're looking at is A, and you want to determine whether A is responsible for D or not. So the counterfactual reasoning algorithm starts out by flipping the question by saying, what would happen if A's value changes? Would it make the problem at D go away? And this is how it proceeds. So first we pick a different value of A, let's say A star. Now A star might be a lower value, for instance. Then we resample B using the newer value of A, and then we resample the other entities, assuming the newer values, so C, E, and D. And then we repeat this sampling process a few times so that if there are any cyclic effects, then those cyclic effects get propagated in this resampling algorithm. So in technical terms, this would be called Gibbs sampling. And after doing the sampling algorithm, you will end up a new value of D, let's say D prime. And you can think of D prime as being a result of changing the value of A to A star. And if this new value of d prime turns out to be significantly less than d, then you can say that a is a root cause, because when you change to a, then according to your model, the value of d also, the CPU value of d also reduces. So a may have caused the high CPU. Okay, and then we just iterate over all of the entities and check them one by one and output those which this algorithm flags as being the root cause. Okay. So just to get back to our running example, this is the relationship graph that I showed you. So the first step, you learn the local metric distribution for each of the entities. So let's say for this flow, you learn the metric distribution of this flow given its neighbors, and then similarly for all of the entities in this relationship graph, and this constitutes the MRF. And the counterfactual analysis, let's say you're trying to determine if this flow was the root cause for the high CPU of the backend. So in your model, you first choose a counterfactual value for flow one. Let's say you reduce the sessions count by half, and then you use the sampling algorithm to propagate that effect to the backend VM. And let's say that your model says, okay, if you reduce the sessions count by half, the CPU utilization will reduce to 30%. So that means that reducing the sessions count will significantly decrease the CPU utilization of the backend VM, and then Murphy will classify this flow as a potential root cause. Okay. So using this analysis, Murphy figures out these three flows, or like flags these three flows as the root cause. One of them is the flow that the crawler machine is sending to the front end VM and sending requests through that flow. And on the other entities, I should say that they are also intermediate entities that relate the root cause, or in this case, which is the crawler VM, to the backend VM. Okay. And I also want to give some intuition of why capturing the structure is important. So in this case, let's say if your problematic symptom were just was VM1, VM1's high CPU, and by chance it also happens that VM2 is experiencing high CPU. Uh, if you ignore the structure, you might conclude that VM2 is the root cause for VM1 because their metrics are going to be very related. Uh, if, for example, you can think of them as replicas of some backend service, then basically they have very similar CPU usage. But that's not the case clearly, because if you look at the topological structure, there is no significant path of influence from VM2 to VM1. But there is a significant path of influence from flow 1 to VM1, and also from flow 1 to VM2. So capturing the structure in this way allows us to eliminate false positives, like let's say VM2 is a false positive for VM1. All right. So that's how we get the root causes in the model. The final step, we generate explanations for the root causes. And this is just a wrapper to help the operators understand the output of Murphy. So to do that, so first of all, I should note that this step will not change the root causes produced by Murphy. This will just assign some explanations to those root causes. So the first step is to label each of those entities by using a certain label based on hard-coded rules, based on their metrics. So for example, you can label them heavy hitter, degraded performance, high drop rate, etc. And then we have hard-coded rules that using which you can trace the chain of influence from the root cause to the problematic symptom. And this chain of influence serves as the explanation trail that you can provide to the operator and say, this is why the root cause may have caused the problem. Okay. All right. So let's see how this works in some applications. So here, this is an application from some from Death Star Bench, which is a suite of microservice applications for benchmarking. And there, as you can see, there are several service components in this microservice app, which are residing on some backend containers. And the problematic symptom in this case is a client who is trying to access a certain API in this application. So this is a social media microservice app, and this client is accessing this service called Compose Post, which I'll just refer to as API 1. And client 1 is experiencing high response times. And it and as it turns out, uh, the root cause is another client who's accessing a different API in the microservice app, but those two APIs share some common services downstream. So when client 2 sends a lot of requests, those common services downstream also get overwhelmed, which then in turn impacts the high response times, or which then in turn causes the high response times for client 1. Okay. So this is in spirit similar to the incident that I talked about earlier, where client two, uh, I mean client, you can think of client two as the crawler machine, and it's causing performance interference with client one. And in this case, if you try to model this, if you try to model this using a DAG, then you wouldn't have client 2 in scope at all to catch this problem. So if you try to model this problem using both client 1, by having both client 1 and client 2 in your dependency graph, then that will induce cycles, because uh, you need to model the effect of client 1 and 2 on the common services, and then back from the common services to clients 1 and 2. Okay. All right. So in this case, Murphy was able to find the true root cause with good accuracy. There are other. So when I say accuracy, in this case means it's a binary metric where we say if Murphy produces the root cause in top five, let's say, then we declare that a success. So the idea is that if a human is looking at the list of root cause leads, the human can decide, I mean, providing the true root cause in the list of top five or some top k is useful to the operator. So by that metric, Murphy achieves pretty good accuracy, whereas others, which are not designed to handle cycles, they don't do well. And in another scenario, which has no cyclic dependencies, so in this case, you actually have a partial order of dependencies. So here there's only one client, and it's trying to access a certain API in this microservice application. And we inject a failure on one of the containers of this application. So the services are naturally this time arranged in a DAG. So that just becomes the partial order. And in this case, both Murphy and Sage now perform well, or like have good accuracy. And that is expected because Sage is designed to handle this case. It has no cyclic dependencies. And both Murphy and Sage use a certain type of probabilistic graphical models. Sage is a little bit worse. And I think the reason, and we think that the reason is Sage is based on some neural network technology for every node in the graph, which requires a lot of data points or a lot of historical data points to train, which we didn't have in this case. So that's why it's about 5% worse. All right. Okay, so those are some evaluation results, and we also tried this in VMware's internal production network, and we found out that Murphy produced significantly fewer false positives compared to other schemes. Um, and only schemes that can handle cyclic dependencies are included because we cannot run Sage in this environment. And I should also note that all of them were calibrated so that they have the same level of false negatives. Okay. All right. So, and then we pitched this to some product teams at VMware who got interested in it. And this is how the product dashboard looks like. So eventually, I mean, I worked with the engineers there and they came up with this. And it has a slightly different name from the research uh, paper, but uh, it's this underneath it uses the same technology. Okay, all right. So that concludes my bit about Murphy. So Murphy, to summarize, if you want to take away one thing from Murphy, it's that you can model these dependencies using weaker notions of neighborhood relationships and staying truthful to the type of dependencies that you have in your system that results in a more accurate analysis. And I encourage you to check the paper for more interesting details and experiments. Okay, all right. So there are so I have these two other systems as well, but in the interest of time, I will not talk about those. So these are about finding gray failures or hardware failures in large data center networks. But let me talk about the current trajectory for failure diagnosis and research in this area. So the so existing research has designed what I call as point RCA solutions, and I'm guilty of this myself. So these point RCA solutions have fixed input telemetry. They use a single algorithm and they capture a narrow class of failures. Even Murphy, for example, it only captures a certain class of failures. But if you look at any large distributed system, there are so many moving parts that you have multiple and diverse sources of telemetry that's available. You have diverse ways in which failures can arise. So you want to reach a point where you have a comprehensive RCA solution, but existing research has only gone into enhancing models and algorithms for these point solutions. And I think, and I'm claiming that enhancing these point RCA solutions, while that is useful because now we have a pretty good understanding of technologies and algorithms and models, a single algorithm or a single point solution will only capture a small class of failures. Whereas on the other hand, we want a comprehensive RCA system that can handle many different types of failures or most of the type of failures that can arise in a large scale system. So so I argue that we need to move beyond these point solutions and we need to take a systems approach for designing this RCA. So typically you will have these multiple sources of telemetry. So for example, you might have telemetry for metrics, for events, for logs, or distributed traces. And on the failure side, you would have many different types of failure scenarios that you would want to troubleshoot. So, for example, this could be a configuration problem. These could be some type of network failures, hardware failures, software failures, performance issues, and various kinds of other things. And you want a root cause analysis system that has a high coverage of all of these failure types. And when you see a new failure type, it should be easy to write a new, it should be easy to include that in your RCA. And if you tomorrow, if you have a new telemetry type, for example, let's say some configuration logs are now available for to the operator, it should be possible to incorporate that telemetry source into the RCA system. And finally, if it's fetching data from all of these telemetry sources that could be voluminous, the RCS system overall should ensure that the system remains efficient and the running time is within reasonable bounds. So this is currently what I'm working on, and it's personally exciting to me because I have been working on RCA I mean, since the early years of my PhD, and I found that no matter how good the root cause analysis algorithm is, it will still only catch a small class of failures. And this was personally uh, a source of frustration for me because no matter how good the algorithm is, it would always, there would be lots of failure scenarios which would be outside its scope. And that is actually also um, the reason why I got into this project. So hopefully I can come back in a few months and talk and share the details of this project with you. All right, so that's the end of my talk, and I'm happy to take any questions now.
Thank you, Dr. Harsh, for a very informative talk. I request the audience to ask your questions, if any.
Oh,
Yes, we have a question.
yeah, Harsh, interesting talk. So, I had one question about how do you identify the metrics to be analyzed? Because there are large number of potential metrics that you could use, and since you are also talking about the entities that are from managed by different administrative domains, right? Like the network and the cloud layer as well as the host are all managed by multiple entities. So how do you identify which metrics to be used amongst all these for the root RCA? I guess once you have the identified metrics, then your model will learn the dependencies or infer the dependency graph, right?
Uh, Correct. So I think your question is how do we model or how do we figure out which metrics to model? So in this case, we had so the monitoring information contained metadata about the different entities in the system. And in this case, because it was a private network, it was all under one administrative domain. But you can imagine you have today monitoring solutions that will collate information from multiple domains or multiple collection points, and they you have a unified database. So this is typically available using standard monitoring solutions that companies use. I hope that answers your question.
Yeah. So one query in your experiments, how did you identify the metrics? Like you mentioned CPU as the major
Uh,
metric, but other than that, what did you use?
So CPU was just an example. We looked at other metrics like, let's say, drop rate for a NIC or memory usage, or for a database node, it would be the amount of storage space. It would be the read throughput, the write throughput. So these are standard metric types depending on what the entity is. uh, and that was also, I mean, that's also a part of the monitoring telemetry. The metrics is, the entities are associated with certain metrics, and we take all of them essentially.
Mm, thank you.
Hello, can you hear me?
Yes.
Ah, so thank you for the nice presentation. My question is regarding whenever in the discussion you only mentioned like one root cause of failure. What if there are multiple root causes of failure? So in that case, the inference algorithm that you develop, will it handle such kind of situations?
So, yes, so this is a good question. How do we handle uh, multiple simultaneous failures? Uh, so multiple simultaneous failures, still the overall uh, overall algorithm can output multiple. It outputs a list of root causes, so it can produce multiple. It's allowed to produce multiple root causes. And if there are multiple entities that are related to the problem or that are independently related to the problem, then Murphy will catch it. But if there is a tricky case where you have two entities that only when you look at them, uh, when you look at both of these entities together, then only then you can spot the correlation, then that is a case that Murphy will not capture. So that's a limitation, I guess. But having said that, we did not see any such case in the production network or in the failures that we injected or surveyed from previous work. So I think that that is a rare case compared to single failures or single entity failures.
So
But yes.
you're saying that in real life, simultaneous failures are rare. Is that
No,
what
no,
you?
simultaneous failures where the failure is where the root causes is evident only when you look at those root causes together. So, for example, it could be that two entities are the root causes and both of them have failed. But when Murphy does the analysis of entity one, it can figure out, okay, entity one is the root cause, and independently when it is running its analysis for entity 2, it can also flag entity 2 as a root cause. But there can be a case where you have to look at entity 1 and entity 2 together. That is a relatively rarer case.
So you can't do like, okay, in the maybe in the first round you remove entity one, and now let's see, okay, what are the other root causes? You go to entity two. You cannot do such kind of root cause analysis in the situation that you said.
I think it's possible. Uh, Maybe like if there is an environment where this happens commonly, then yes, I mean the algorithm could be modified to do something like that. So this is actually, you bring a good point. So we do this for one of my other projects, in fact, where there is a large data center network which can have hundreds of thousands of components, and their simultaneous failures are much more common. So there we actually have analyze each component, analyze the components one by one, and when you identify a root cause, you take that out, and then you still are, and if there are still unexplained um, failures in the, or let's say unexplained problems in the system, then you look for additional root causes. So yeah, that is definitely one approach.
Thank you for your time.
Any other
Okay, I
question?
guess that's it.
I had one
Oh,
more
Do
question if there is time. I-
yes, yes,
So,
sure.
the problem with many of these systems is the availability of labeled data set. So, how dependent is this RCA on the labeled data set, and is it able to capture the issues beyond the labeled problems that are flagged?
beyond, oh, okay, so there are two questions. One is that how do we deal with the problem of having a labeled data set? So getting a labeled data set with failures, that's a very, very difficult thing to have, especially if you are looking for a large data set. So we were able to collect uh, about 10 to 15 of them from the tickets. So we just, manually looked at all of the tickets that, all of the Jira tickets that were there. And we could mine 10 to 15 incidents out of it, along with the ground truth that was identified by the operators. And now I should say that even that is not an accurate picture of the ground truth, right? So the operators may have misjudged a particular incident. So for example, there was a case where they rebooted all the VMs of the application, but the root cause was probably only one of them. So there is no getting around this problem. I think you need some simulation or emulation to inject failures and create these data sets, or and then you have like a small validation data set from your production or whatever your real environment. Now, the second question was what happens if the anomaly itself is not identified? How do we do that, right? That was your second question. So for example, how do we even know that there is a performance problem? And this is out of scope for Murphy, but this is also an interesting problem, I should say. So this is a good question, because your performance problems can arise in complex ways. So for example, it could be that your performance problem arises when your load is low, but your latency is high. Now, that's a weird issue that I have seen in production, but you need sophisticated algorithm to detect such kinds of complex anomalies. But yeah, that is out of scope for Murphy, so I think that would be a separate paper probably.
Mhm. Yeah, actually, Vashikar had presented another approach a few years back in the same seminar series around synthesizing some of the data sets using GANs. So, are you looking at something like that also to enrich the data, training data
Yeah, yeah.
probably?
Yeah. So we have considered it. I think so. There are these CAN-based solutions which can generate data sets based on some labeled examples. So the problem there is that it's very hard to get the structure right. For example, let's say there is a user session, right? So there is a pattern of events, and you, that pattern, there is a sequence to the pattern. Like there is a sequence of, let's say, request accesses that are made to the backend network, and if you use a GAN, it inevitably does not have the same. There are some inaccuracies in those sequence patterns, because of which we decided to not use it and instead use a simulator. Uh, so for my other projects, we use simulators. For Murphy, we decided to run some benchmark applications of our own at a smaller scale and inject failures in those applications. I hope that answers your question.
Yes. Yeah. Thank you.
Okay. Since I hope there are no more questions, I'll end the meeting. Thanks again.
Okay. All
And
right.
thank you everyone for attending.
Okay. All right. Thank you for having me.